Objective 4, let's jump on it. Simplifying exponential expressions involving rational exponents. There's a lot to unpack there. Simplifying exponential expressions, that's easy. That's what we've been dealing with. Involving rational meaning the ratio null numbers, meaning our numbers that can be represented as fractions that only have whole number numerators and denominators, exponents. Okay, so let's just maybe write ourselves a little bit of a note here to the side to give us an idea of what we're talking about. Simplifying exponential expressions. So we're taking numbers. You could choose X or A. Maybe I'll choose A since we've been using A. I'm starting with a number. I'm going to give it an exponent so that it becomes an exponential expression. And I'm going to involve a rational exponent. So now I've got a fraction exponent. Okay, so that would be maybe something like this. We could say that this is exactly what we're about to figure out how to deal with. What happens when there's a fraction up there? Well, we're going to couple this with objective 5, which is simplifying the radical expressions using the product rule. So again, radical expressions are anything that has that root symbol. So to keep it from just generically being a square root, we're going to use an n there and say that is what we're going to say is our general form of a radical expression. So just a little bit of preparation there. So sometimes it is easier to write the nth root of b as b to the 1 over n. That's a little bit odd. We're gonna see why that's true, and also why we would ever want to do that. Isn't that just adding complications? Well, let's take a moment and see. Let's look at numbers, for example. Let's take the square root of 8, and as it's written here, it's to the 4th power. So that means that I'm going to multiply it by itself 4 times. Well, let's think about what that would be. I have the origin of an 8 square that is being multiplied by another origin of an 8 square. That should get me an 8 square, right? Again, if we want to visually, we can think of it as the square root of 8 times the square root of 8. And if I'm talking about the origin of this square, the square then would have to be 8 in order for that to be the appropriate origin. All right, so I've got 8 is the first thing I'm going to get. And then I'm going to get an 8 from the second pairing as well. That's going to give me a total of 64. Now, why would that be expressed as 8 to the 1/2 to the 4th? Well, remember from last time, what we were doing with exponent rules is we said 8 to the exponent to another exponent could be thought of as multiplying those exponents together. Because essentially what you're doing is you're repeating the grouping that you have. Well, that would be 8 to the 2nd power, and that would be 64. Wait a minute, that seems odd, like it shouldn't have connected. Let's see if we can break down what's happening. If you imagine a square root as being a component of multiplication, so essentially one level down from multiplication, like we want to have the 8, but I have the square root of 8, and I'm going to use that to get to the 8 with multiplication. If we imagine it as kind of like this layering, then when I talk about having 4 of these half multiplies, that's an improper word. We're going to try to move away from that quickly. But if we have 4 of these half multiplies, it's almost like I have 2 of the whole multiplies, which would be 8 times itself. Okay, so we can think of these fractional exponents as being one step backwards, one halved process in the multiplication. This is a little bit odd, but if we allow our model of logic to roam freely, it kind of makes a little bit of sense. It's like we're going to be someplace, but I need 2 of them to multiply and interact to get me there. So let's talk about those in halves. We're going to play around with that a little bit more to make that comfortable. In either case, we can create what we call the product rule of exponents. Well, that's exactly what we have just talked about, right? This idea that I can think about repeated groupings of exponents as being multiplication. Okay. Let's discover some shortcuts, shall we? That's a lot to keep in our mind, so let's see if we can move through the logic in a faster process without losing track of exactly where the logic came from. So I'm going to give you this question to start with. I have a cubed root of x to the 6th. We can break that down into its meaning. It means that I am multiplying x times itself 6 times, where x is some real number. It could be negative, positive, decimal, fraction, nice fraction, crazy fraction. I've got x to the 6th, and I'm looking to say that that x to the 6th is the size of a cube, and I would like to know what the origin, the original side length of that cube was. What did I use to construct that thing? Well, that's where we get this notation right here, is it's me expanding from the inside outside, the meaning behind my notation. Is that okay for me to write that exact same thing this way? This can be a little bit weird. Let's test it. Okay, so now maybe I want to look at this and I say that I have multiplication happening. And so I'd really like to know that if I took cubed root of x times x times x, and I multiplied that by the cubed root of x times x times x, what would I get as a result? I'm going to leave that one for you to just think about for just a moment. What do you think we would get as a result? Is this a fair connection here? All right, so now that you've given your opinion on that one, I'm going to kind of come to this logic from a roundabout way. I'm going to say that maybe that connection isn't as immediately apparent for me. So I'm going to say instead, let's look this way. Is it okay for me to say that what I'm going to be doing in this process, similar to above, is that I have 6 of these x's being multiplied together, and I'm going to be finding groups of 3 to pull out? I think that that's pretty fair, because if you again remember all the way at the top in our numbers where we came from, that sometimes when we were trying to figure out what are the side lengths, we would say that if I had a 5 on both sides, that I could multiply that to get us 25, and the 25 would be a size that would help me grow into the original number. So it's almost like I'm factor treeing things out. I'm looking for what are the origins of all of these exponents. So I think that I'm more comfortable with saying I could take this repeated multiplication and say that really what I'm trying to do is I'm trying to take these 6 and I'm trying to chunk out groups of 3. Well, let's write that as division in our exponents because that makes things much, much easier. Okay, so I'm comfortable with the x to the 6 over 3. Perhaps then I write it. Means is again that I have used the product rule of multiplication, or the product rule of exponents, and I've said that instead of saying I have 6/3, that would be like I have 3/3 and another 3/3. So essentially we're grouping, we're chunking out these groups of 3 repeated multiplications. So I've got the 6 to the 3rd, I've got now 3 to the 3rds. I know 3 to the 3rds is going to be 1 in either situation, so that gets me down to x squared. Okay, so I've almost like this process of simplifying better. Can I roundabout connect these two? Absolutely. The multiplication right here, I can see that immediately. The cubed root, that's essentially like I'm trying to find its components. I'm trying to go some steps backwards to say if I had a thing and I used it as my component for multiplication 3 times over, would I get back to my original? Absolutely. There's my cubed over here on the left, and here is my 1/3 on the denominator. Oh, and here's my numerator right here, my repeated multiplication, so that's the top. And then the left hand part is just that entire idea said twice. Okay. Well, now let's see if I understand this right column a little bit easier. Maybe I can detect again to the left-hand column. Here I have my x to the first power. Then they give me x to the first power. I love that. X cubed and then cubed rooted is what I know is the meaning behind here, because it's like I'm repeating the multiplication and then I'm trying to chunk out the parts of that multiplication. So that's why I can write it as the cubed root of x being multiplied by itself 3 times. Well, then the same simplification occurs down here, where the repeated multiplication 3 times and the root of that is just x. It's like I have 3 of these that I'm using, and I'm trying to figure out what's the starting block. Well, it's just one of those is my starting block. And I think that's a pretty easy connection no matter which way you go between these two. So what I want to kind of point out with this example is that you can go from this start to this simplified expression by zigzagging through any of these equivalent expressions. Any of them at all. So I want you to choose your favorite and then become more and more comfortable with the other ones as you develop your mathematics. For me, I'll let you know quite transparently, I think that this cubed root of x to the 6th, I like to think of it as starting here, where I'm trying to say, I know that I'm going to be multiplying things in groupings of 3, and I would like to figure out how many of those starting blocks I need. Well, how many times do I need to repeat multiplication for groupings of 3 in order to get x to the 6th? I'll show you another way we can look at it. What if I just knew that if I start with 2 of these and I repeat that 3 times, so there's the second repeat, and there's the third repeat, that's going to get me x to the 6th. So if I said, what is the cube root, what is the origin of x to the 6th, I would say it would be one of these pairings. Think through whichever of these you like, become comfortable with it, and understand that we can bounce between the different perspectives to try to communicate more effectively. All right, let's finish up this last page here. So let's apply some shortcuts and tackle monstrous problems like this. Where do we even begin? I'm going to say that perhaps we begin with the meaning. Let's look at the very beginning. I have stuff inside the parentheses, complicated stuff inside the parentheses. I'm going to be raising that to a fractional exponent. That seems difficult. I don't know if I want to do that in my calculator. I can't do it in my calculator. I have variables. Can I do it in parts? What does everything mean? How can I break this back down? Well, I know that the fractional exponent is really 2 things in one. It's a square, because I have 2 at the numerator. It means that I'm going to be trying to use this to repeatedly multiply by itself. And then I'm going to be doing a root. I've got a cubed root, and that's what I mean here in the denominator. So I've got a cubed root, and so essentially saying that after I've used it and then multiplied by itself twice, I need to figure out what is the origin as if I had done it 3 times. Okay, that's a little bit odd. On the inside, I have a lot of complications. I also have some negative exponents. I'll tell you what, this is probably a good time for us to use the rules that we've spent so much time developing, because we know that the rules are logical, and so I don't have to apply the meaning each and every time I have a problem. What can we do for rules? Well, I'm going to let you know that having an exponent to an exponent is really bothering me. That seems like a lot of work. And I can't do anything inside the parentheses, because inside the parentheses, I can't simplify x and y's. I can't do 125s. I have a negative exponent, but I can't move it to the bottom because it's inside parentheses with stuff on the outside of it. So let's pull on the only rule I think we can, which is let's take advantage of our exponents to exponents rules and simplify this on up. So we know that, for example, a to the b to the c is equal to a to the b times c. If I'm comfortable with this idea of the repeated groupings, and I'm comfortable with the idea of fractional exponents being no different than other exponents, then I can absolutely just multiply those exponents on through. So it's as if I have this 2/3 on the outside, and I'm multiplying it by the exponent that the 125 has. I don't see an exponent the 125 has, so that must have meant that there's only one of these 125s. So I'll do 2/3 times the 1, that gets me 125 to the 2/3 power. Okay, I'm okay with that one. The next one gets me x to the 4th, and then I'm multiplying that by 2/3. So I'm just going to write that as 4 times 2/3 for right now. Notice the 4 goes on the numerator, because on the numerator of the fraction is going to be our multiplication. And then I've got 2/3, and I'm going to multiply that by the negative 1/4. That's going to be the exact same logic. So that'll be 2 on the numerator, that'll be 12 on the denominator, because I've got a 3 on the denominator, and I'm multiplying that by a 4 on the denominator. Okay, and we got to keep the negative. Great. Let's try the bottom. The bottom is going to be so much easier, the denominator here. The denominator will be x squared times that 1/3, gets me x to the 2/3, and then y to the 1/3, because there was only one y there, so that would be 1 times 1 to the 3rd. Okay, so I'm feeling okay with this one. This one took a lot for me to kind of feel comfortable with that first line of work, but I think that I'm okay with the idea of saying I had layers of exponents. That was bothersome to me. Let's try to get rid of that. What can we do from here? I would say from here, we probably want to start to simplify wherever we can. There's no reason I can't type this 125 to the 2/3 into the calculator. If you did want to put it in your calculator, you would want to be very careful with the parentheses, and you would do something like 125, your little caret button, and then you would want to make sure that you group 2/3 as being the entire exponent. Well, that's difficult for me to think of on the paper, so maybe I write that using my traditional radical. So now I've got the 3 as the index, the 125 as my radicand, and then the 2 is going to be the square that I am going to apply to that afterwards. You could think of it the other way around. We could think of it as 125 squared cubed, but I just chose to do it this other way. Mostly because I know that the cubed root is going to bring that number smaller, and I think that's going to be much more manageable on my paper. Okay, so we've got that. Everything else looks like we're just going to simplify through. X to the 4 times 2 over 3 is going to get me x to the 8/3, y to the 1/6, keep that negative, x to the negative 2/3, where'd that come from? Oh, it came from the denominator. So maybe in this step what we're trying to do is get rid of the fraction bar. Maybe having negatives and positives all with the same fraction bar is a little bit difficult. So let's put it all the same. Let's put it all in the numerator, and we'll let the negatives play out as our memory tool, as our maintaining the meaning of the original expression. All right, let's keep going. What do we have in this next one? Cubed root of 125. That's a rough one. Cubed root of 125. What times itself 3 times gets me 125? Play with it in your calculator. You're going to see that it's going to come out to the number 5. So that's the cubed root of 125 would be 5. And then we took that number and we had it squared, right? This was the original expression. Cubed root of 125 quantity squared gets me back to the original meaning. Well, 5 squared is 25. So a lot going on there. We cube rooted to get it down to 5, and then we had the square because that was in the original expression. So that's the 25. 25 comes from doing both of the meanings in the fractional exponents. Let's see what we can do here for the x's. X to the 8/3 times x to the negative 2/3. Okay, so we've got exponents being multiplied together. No, correction. We have exponentials being multiplied together. We have x to the 8/3. I can multiply that by x to negative 2/3. And we remember from our rules before that if I have a to the b times a to the c, that was equal to a to the b plus c. Why was that? Because I had B groupings here, I have C groupings here, and if I combine them both together, I have B and C groupings. So I can do the exact same logic model with these up here and say x to the 8/3 and then x to the negative 2/3 is going to get me x to the 8/3 minus 2/3. If you need to write yourself some more notes here, go ahead and do it, but I want you to parallel back into your notes and realize that it came from the exact same rules that we spent so long developing. So I have 8/3 minus 2/3, and that's where I have this expression. The exact same logic applies for the y's now. Y to the negative 1/6 and y to the negative 1/3. Well, if I'm combining both of those together, we know that from our rules, which come from logic themselves, that we are allowed to combine those exponents using addition and subtraction. Well, the subtraction here is just inherent in the negative 1/3. Okay, so I've got adding negative 1/6 and adding negative 1/3 gets me negative 1/6 and negative 1/3 both in the exponent. Okay, so far so good. Lots to break down here. Next problem, 25 stay the same. Love that. 8/3 minus 2/3 gets me 6/3. Love that. Negative 1/6 minus 1/3 gets me, that's a difficult one. Maybe we need to do some side work for that. Negative 1/6 minus 1/3. I can't combine those because I don't have a common denominator. I'm talking about apples and oranges here, right? If I said take some sixths and combine them into thirds, we're not talking about the same thing. But if I said take some sixths and then take away some more sixths, you'd be like, oh, I know how to do that. That'd be as if I had so many things and I was taking away some more things. Okay, so let's write this differently. Negative 1/6, and then instead of negative 1/3, I could think of that as having negative 2/6. Okay, the negative 6. Perfect. That's where I get that from. So we're slowly simplifying, slowly using our rules, maintaining the logic and the meaning. 25 stays the same. X to the 6/3 means I was taking x, I was multiplying it by itself 6 times, and then I was taking out chunks of 3. So I had 6 and I was taking away 3. Oh, that's just like what we did up here. Okay, that's just like what we just did up here. X to the 6, and we're taking away chunks of 3. That gives us x squared as our beginning base. Okay, and then I have y to the negative 3/6. So that's as if I multiplied y by itself 3 times, and then I was trying to take away the components so that there were 6 components. That'd be as if I had a bunch of half components there, if we want to loosely use our metaphor. If the metaphor is not helpful anymore, we can stick with the numbers and the logic for it, and then we keep the negative idea. Okay, the very last one would just simply be, I'm trying to combine all of this together and hopefully make it a little bit more simple. So I have the 25, and I'm just simply multiplying the 25. In fractions, we would say that means it goes in the numerator. So I have 25. X squared is just simply being multiplied, nothing fancy with that one. That's also going to be going on the numerator. Y to the negative 1/2. That's going to be the 1/2. I know that means I have like a part component. That's your square root, the square from the number 2. And I have only one of those square roots. Okay, so I have one square root, and then the negative part of the exponent means do the opposite of multiplying. That'd be division. So I have a square root of y that I am dividing. That's why we would put it on the bottom right here. Oh, golly, I think that's about as simple as we can take it. So I would agree with this work here. I would say that this looks significantly more simple than this, much more easily relatable. Something I would definitely want to present to people more so than the original. So 25x squared over the square root of y is what all of this mess is equivalent to. Okay, very nice. Let's go ahead and finish up this section with the last objective. So let's check our understanding. Can we simplify these expressions using all of these rules that we have? You have a lot of different paths you can take this on. Do you want to start with making exponents into negatives? Do you want to start with making square roots into half exponents? Do you want to start combining things with the product rule or the exponent rule or the quotient rule? What exactly do you want to play with? And I encourage you to do just that. I want you to play with it. I want you to try multiple perspectives. Write down at least 2 different ways to solve this problem in your notes. I will help give you one of them. So the way I look at this problem, so we have the square root of 3x to the 9th over x cubed. What can we do? The first thing I'm going to see that pops out immediately to me is I have x to the 9th, and I'm dividing by x cubed. So we can think of that again as x multiplied by itself repeatedly a whole bunch of times. And by a whole bunch, in this case, I mean 9 times. So I've got x multiplied by itself 9 times. I'm dividing by x 3 times. And we know that's going to cancel out 3 of these x's from the 9, leaving me with 6. So I could probably simplify this problem just right off the bat by saying I have the square root, I haven't done anything with the 3, I've done anything with the 8, but multiplying by x 9 times and then dividing by x 3 times leaves me with 6 x's. Okay, great. What else can we do? There's a lot to manage here. I'm going to say that I could probably rewrite this as square root of 3 over 48 times x squared, or excuse me, x to 6. I like that better. And then I'm looking for these square roots. The square roots are going to be a little bit hard. The 3/48ths, what can we do there? We could rewrite this saying square root of 3. So I want to figure out what number times itself gives me 3. What number times itself gives me 48. And then what number times itself give me x6. Now remember, we can don't say distribute. We can use the square root symbol and we can apply it to the numerator and the denominator and the x to the 6th for the same reason we had very early on in this packet. Remember, we were trying to figure out what we could do with this 1/27th. Well, we could affect the numerator and affect the denominator with the same logic of saying that I'm going to look for what times itself gets me the denominator. The square root of 3, I can tell you already that one's not going to be able to be simplified because 3 is a prime number. So that's just going to have to stay as square root of 3. Square root of 48. 48, when I'm trying to square root, remember that we could use our factor tree here. Let's do 48. That would be 2 and 24. That would be then what? 2 and 12. That would be 2 and 6. And then we could say 6 would be 2 and 3. So I could think of the square root of 48 as being the exact same thing as the square root of 2 times 2 times 2 times 2. That's 3. Okay, and then I have a square root of x to the 6th. Well, we should just get ready to simplify this on through. I have cube, or the square root of 3 at the top. On the bottom, I have 1 square, right? I have 2 times 2, that gets me a 2 square. And so I asked what's the origin of 2 square, that would be a 2. I have another 2 square, so the origin of that would be another 2. And then I have a square root of 3. Okay. And then I'm looking here to say what is x to the 6th square rooted. You could think about that. What times itself gets you x to the 6th? I'm also going to remind you that we have rules here. We could do x to the 6th to the 1/2 power, and then think about multiplying that on through. That would be cube root of 2 times 2 would be 4 root 3. And then x to the 6th to the 1/2, we could think of that as being x cubed. And now we've got cubed, or the square root of 3 divided by the 4 times the square root of 3. Those are the same thing on the top and bottom, nothing but multiplication between them. We can simplify that, and I think we'll be just about finished. X cubed over 4. There you have it. Even unrelated numbers like the 3, the 48, if we're trying to combine those together and simplify them, we're allowed to take what look to be very complicated expressions and write them in a way that is simple, easy to communicate, and we can connect the two using nothing more than the logic that we modeled earlier, now formed into shortcuts so that we can more easily use them with the problem at hand.